75 is a homework problem, so I'm going to do 74. I'm going to try to do 74. Half-pound ball is shot from the spring device shown. Aha! It says spring. Must be energy, right? No. I've been known to give final exam questions and draw springs on there and ask a different thing and watch you do energy. Love it. Love it. Okay? Just because there's a spring doesn't make it an energy. I'll change the question and show you. All right, 4-pound ball, the spring device. Spring has a stiffness of 10. 4 chord C. Let's see. Keep the spring compressed 2 inches when no load is on the plate. The plate is pushed back 3 inches from the initial position. If it is then released from rest, determine the speed of the ball when it travels 30 inches up the smooth plane. Okay, is this an energy problem? Yes, why? You're going to ask how many questions? Well, how many questions are you going to ask to see if it's an energy? You should rule out energy first, because if it's an energy, it's usually easier to do it with energy. Not that you have to, but it's usually easier. So if it's an energy on the final exam, you want to grab it and do it. Okay? And but not all of them will be. So what you want to do is look at it and say, no, it's not an energy, darn it, I hate that guy. And then you go back to the old stuff. Okay. 3 questions. Number 1, is it the time, in whatever order. Is it the time spanner? Is it the time spanner? Yes. Yeah, because it started here. What's it doing when it's up there? It took some time for that to happen. Yes, it's a time spanner. Do you care how long it takes? Because it's very difficult to find out how long something happens using energy. Do you care about how long? No? Okay, good. Thank goodness. Can you get the energies or the works for all of the things that cause energy to come out and go in? Well, let's list out all of the forces, because the only thing in this class we have to worry about are forces, right? If it was a real world, we'd have pumps, we'd have all kinds of weird stuff that could be happening, and you have to look at them and go, yeah, I can get that energy, yeah, I can get that one too. But for this class, it's just work. It's forces and distances. Okay, so I'm going to list the forces. Free body would help if you want to. There's gravity on the ball. What else? Oh, there's a normal from the plane, right? There's I'll call it a push from that plate, right? There's a spring. Let's not forget that guy. What other forces are there that I need to think about? Friction? Is there friction? No? Okay, thank goodness. Anything else? I can't think of anything. So let's check them off, okay? Can you find the work done by gravity? The answer is yes, because you have a potential energy for gravity. You can always find the energy. Now, your book divides it. I don't know why they do this. I think he's a closet physicist or something. But he separates the book out. In the first part of the chapter, he does everything with gravity, and he's doing the work of the gravity and all that mess, right? Good, great. And then he goes in and he does conservative forces or something, and now he brings in potential energy. Nobody does it like the first. Nobody does it like the first chapter. No one. There's no reason to. It's absolutely absurd. I don't know why they do it, but they do, right? I'm always going to use potential energies. Always, 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 always. That's what I recommend you do, okay? So if I have a potential energy for the force, I don't have to worry about the work, because the potential energy takes care of it, okay? Gravity, I have a potential, so I'm going to check it off and say I can do that one, okay? How about the normal from the plane? Do you have a potential energy for a normal force? Is it in the book anywhere? No. Can you find the work of it then? Yeah, you can. Yeah, you can. Now, okay, here's the incline. That's the motion, right? The motion's this way. Which way is the normal force? Perpendicular. Okay, how much of this is pointing in that direction? None? Okay, then what's the work? 0. Okay, so you can do it, right? So let's check him off. The push of the plate. Okay, here's the ball. Here's the plate. They're pushing on each other, right? There's a force there, right? Does it move? Yes, it does. Uh-oh. Is it horizontal? Oh, yeah, it is. But it cancels out. Why? Because this guy pushes on him with, I don't know, N. And the motion is this way. The N is this way. That's negative, right? And this guy pushes on this guy with N that way, and they're going to cancel out. You see that? Whenever they're together like this, no matter what they're doing, cancels out. Equal and opposite forces, no matter what weird stuff it's doing. Because the forces are equal. Right? And the motions, one is lined up and the other one is opposite. So one's going to be positive, one's going to be negative. See how that works? Okay, so can you get the work done by this push plate? You bet. What about a spring? Well, if you want to do the first part of the chapter, man, you got your hands full. Oh, no. I'm going to use the second half where I'm using potential energies. Do you have a potential energy for the spring? Okay, then I can do it. I don't need to worry about it. Did I check them all off? Can I get the work? Yes, I can. Okay, is this a good energy problem? Yes, it is. Let's use energy. Okay. Okay, so do I have any energy coming in or going out? Well, I checked them all off. They're all zero, right? So I got nothing. Got nothing. So that's zero. Equals. What is it equal to? Final minus initial. Final minus initial. What's the final energy? Okay, the ball is shot, blah, blah, blah. Released from rest. Determine the speed of the ball when it travels 30 inches up. Okay, tell me about the energies that are there. Somebody's got to have them. Does the ball have some energy? He's got a speed, right? It might be zero. The answer might be zero, right? Might not be. Does he have energy if he has the speed? It's not potential. Kinetic. Yeah, if he's moving, that mass has got kinetic energy, right? So at the end, I'll put a parenthesis. This is the end, okay? I've got 1/2 mass of the ball times the speed of the ball squared. There you go. Anybody else got some energy? Does the ball have other kinds of energy? What other kind of energy does the ball have? Gravity potential. Doesn't it have gravity potential? You can choose the zero gravity potential anywhere you want. Where would you like to choose it? At the origin, right where he starts down there? Is that a good place to put it? So this would be zero gravity right here. Zero gravity energy. Okay, so how much gravity energy do I have? You remember the formula? MGH. MG. What's the H? It's the distance you moved, correct? Is it the distance I moved? No. It's the vertical height above the zero. Doesn't matter how you got there, but where are you? How high are you? Makes no difference how you got there, but where are you? Can you give me the vertical height? Okay, and because they gave me the distance that he went up, right? So it would be 30 inches. And I'd be careful. I would put everything in feet, but it's up to you. 30 inches. Okay, so it'd be 30 over 12. Now put it in feet times what? Sine of 30. Is he above or below the zero? Above, so that'd be positive energy. Anybody else got energy? Let me ask it another way. Who else has energy? The spring. Unless he's at his free length. But he's got those 4 cords holding him down, right? Okay, so if he's bent, then he has energy. How much is the spring energy? Oh, it's equal to 1/2 K. Watch the units. Watch the units. 1/2 K times what? The technical word is squish. Okay, that was a joke. That was a bad joke. It's the squish of the spring. How much is the spring squished? Well, we have to read carefully because they told us. They say that the strings pull him back 2 inches when there's no load, right? So if the strings were not there, he would be a certain length. The strings pull him back 2 inches. So isn't the squish 2 inches? Okay, I'm going to convert it to feet or whatever. Is it K? Yeah, well, watch out for the units. I'm going to put everything in feet. So it'll be 2 inches. 2 feet, right, squared. That's the final energy. Anybody else got energy? Nope. Okay, so that's the final energy minus the initial energy. Initially, does the ball have any energy? What about kinetic? 0, because he starts off at rest, right? No kinetic at the beginning. How about gravity? Does he have any gravity energy? No? How about spring? Okay. How much is the spring squished? 2. Is it 2? Is it 3? 5? Is it 5? When the strings are all the way out there, how much have you got? 2. Okay, and then what did it say I did? I pushed him back some. How far back did I go? I did 3, right? So how much is he squished? 5. He squished 5. He started out this long. I pulled him back 2 and put the strings on him. Then I pulled him back 3 and let him go. So he's squished 5. Right? So I should put in a -5, right? Shouldn't put a +5, right? Doesn't matter. You're going to square it. Doesn't matter. What matters is how much is he squished? 5/12. Make sure you watch the units. Watch the units. Watch the units. Okay. Anybody else got energy at the beginning? No? He's got to be somewhere, right? So spring. No, that's it. I got it all. How many unknowns? 1. How many equations? Did you solve it? Okay. See how easy it is? Now here's where you're going to make a mistake. Okay, this is where you're going to make a mistake. You were going to put a 3 in there for the initial energy, weren't you? You admit it. You were. So that's where you're going to make a mistake. It's not that you don't know how to do energy, it's that you get careless and you read it quickly and you just slap numbers in there because you want to go to the next one. Be careful. Okay? Be careful. All right, suppose I want to change this on the final exam. I'm going to show you the same picture. I'm going to show you almost everything exactly the same. And I'm going to change this thing right here. Determine the initial acceleration of the ball. Is it an energy problem? Is it a time spanner? Not a time spanner, is it? Everything else is the same, right? And after grading the exam, some of you have got solution made. I know you do. I know you do. But if you notice, I changed one of the problems. You probably didn't. Because that's how I knew you had a solution made. Because you solved the solution made problem, not the question I asked you. And how did I fool you? I think I fooled you because I showed you the same picture I left most of the words the same, and I just changed just 2 or 3 words. Gotcha. Okay. Gotcha. Solution manuals are fine to learn with if that's what you're using them for. If you're bringing them into an exam and copying it, watch out. Okay, watch out. It's really easy to change it, and you won't know it. Okay, unless you know how to do dynamics. Okay, so you see how easy it is for me to, right? But I told you this, I've warned you about this, and I told you how to read the problem so you know what to do. So it's not like I'm throwing you to the wolves. I just want to make sure that you are learning dynamics and not just copying something out of the book. Okay? Everybody okay? Bless you. Shall we go on to another problem? Or any questions on this?
Why is its initial acceleration, like if you change it to initial acceleration, why is it like...
Okay, why is this not a time spanner? Right? It's got to be 3 things. It's got to be a time spanner. You have to be able to get the work. You can get the work, not a problem. Do you care about time? No, I don't care about time. Okay, so the only one that you're missing is it's not a time spanner. And the reason that it's not, the reason you want it to be a time spanner is because you have to have a final and an initial. So why is it this is not a time spanner? Well, the ball's back there, it's compressed down. I let it go right then, bam! I want to know something about it. Did any time go by? No, it was immediately. As soon as you take your hand away, I want something right there. Time did not go by. You can call it whatever you want. I call it time spanner. Okay? So it's not a time spanner. So if you try to use energy, you're just wasting your time. Right? You're wasting your time. You'll never get anywhere. Never. Okay? So just because it looks like a spring, just because it looks like something you did on the homework, just because it looks that way, doesn't make it that way. Right? You've heard that expression, if it looks like a duck? Well, in this case, that ain't true. If it looks like an energy, may not be. It's got to follow those 3 questions. Everybody okay? How would you do this if I were to ask that? Well, what you need is you need that the spring force is equal to the spring constant times the deformation. Okay? Spring force equals spring constant times deformation. So let me ask you this. What is the initial force on the ball caused by the spring? K times what? The squish. And how much is the squish? 5 inches. Okay? So the force from the spring initially is K times 5. And watch the units. Right? So now that you have the force, you can draw a free body diagram. Bing, bang, boom. It's a real simple problem. Right? If you know what you're doing, it's a real simple problem. Both of them are. Energy or the other one. But if you just jump in there and say it's the energy, you'll end up solving the wrong thing and giving me the wrong answer. Questions? You okay? You ready for the final one? Bless you. Okay, pull out a sheet of paper. I'll give it to you right now. No.